Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Good evening, Dr. Abdul Aziz, and good evening, everybody. I am Muhammad Mansour. I'm working as a QC engineer in Aquapipe company. And today I'm going to present my project in quality management course, CEM 515, which is GRP statistical process control. This is my presentation outline. First of all, I'm going to give a brief introduction about the company and the product. After that, I will go through the process description. Then I'll give a background about the case. Then I'll go through the process map, the data collection, the data analysis, and the cause-effect diagram. Then I'll present the modified process map, and then give the recommendations, and I'll conclude my presentations. Aquapipe is a pipe manufacturing company. We started the commercial production in 2009. Aquapipe is a sister company of Aquapower International. Aquapower International is the biggest provider for water energy in Saudi Arabia. Our products are mainly, as I said, pipes. We have concrete pipes in our plant in Rabal. And in our plant in Dammam, we have fiberglass pipes, which are classified into two types: GRA, which is glass reinforced epoxy, and the GRP, which is glass reinforced polyester, which is the GRP is the type of pipe which will be under our study. For GRP pipes, we use the CFW, which is continuous filament winding process. In continuous filament winding process, as a composite pipe, GRP as a composite pipes, it is contain of several raw materials: the silica sand, the polyester resin. As a glass, also it is classified into two classifications: hoop proving and the chop proving. The materials are added as per the design values. The design values are coming from the design department, from what we call a control summary that is provided by the design department. These are the raw materials. This is what we call the hoop proving, and this is the chop proving, which is originally a hoop proving, but it is cut and it becomes like this after cutting. This is the resin, polyester resin, and this is the silica sand. This is a drawing of our machine. I will talk only about the last layer. Actually, it includes of several layers, like the mandrel, the discs, the aluminum beam. But the most important thing is the last layer, which is the steel band. The steel band, its job is to rotate all over the machine like this, and coming out. While it is rotating, it's going out and bringing the pipe with it outside the machine. And when it reaches to this level, as you can see here, the steel band will leave the pipe and then go back, and then return here to the beginning and start again rotating, and so on. So this is the mechanism of the machine. This is from our plant, real production. As you can see here, the raw material is falling on the mandrel. This is resin falling here. This is also resin, another stage. Behind here we can see sand, this white thing. And there also behind we can see the chop proving. And these little ropes are the hoop proving. This is another view from the other side. Here it is clear the hoop proving that is coming on the pipe, rotating on the pipe. And this is a finished product. As a case background, first of all, we noticed that we are having high thickness values in the coming pipes. The thickness is formed, as I said, by adding raw materials. So high thickness means that we are consuming more raw materials, which means that we are losing money. So in this project, I'm going to focus on the diameter 2800. Along 6 months, we produce about 600 pipes of this diameter, and I'm going to use this data for my project. This is the process map. First of all, we get the control summary, the release from the customer, from the design department. Then after getting the control summary, which contain all the technical details for production, we set up the machine. After that, my department, which is the QC, will check the mandrel outside diameter to confirm that it is matching with the pipe, the required pipe ID, which is inside diameter of the pipe. After that, we before production, we check the raw materials like resin and sand, and so that we make sure that it is good for use. Then we carry on production. While producing, the machine operator will check the thickness of the pipe. And here we need to decide whether the pipe is within tolerance or not. If it is within tolerance, we'll continue production. If it is not, we'll see whether the thickness is higher or lower. If it is lower, the operator will add some raw materials. And if it is higher, the operator will reduce some raw material. And this point, reducing raw material and adding raw material, based on what? This is a main problem, that the operator sometimes is adding just as from his opinion, he's thinking about something and deciding on his own. In data collection, first of all, I need to state that I faced some difficulties in collecting the data for these pipes. Not having an ERP system was also was increasing the difficulty actually. As I said, we have 600 pipes which represent the data points, and I separated these 600 pipes into groups with subgroup. Each of subgroups is with size 20 data points. This is the control chart of the thickness for these 600 pipes. As you can see here, the desired value is 34.29 millimeter, and what we are getting is 35.2, almost 0.2 millimeter. So the difference is almost 1 millimeter extra, which means more loss of money. So if we go deep into the raw material consumption, we'll find that for every raw material, this is for chub, for example, the desired value for chub is 50 kg per meter, while we are getting average of 49 kg per meter, which is almost 1 kg lower than specification per meter, 1 kg per meter lower. For hoop, if we go for hoop, we are having almost similar values. The design value is 56.8. The actual average value is 57.38 kg per meter also. Here are the main problems in resin and sand. For resin, we are having about 13 kg per meter, lower than specification. The specified value is 152.61 kg per meter, and the average value is 139 kg per meter. And for sand, we are getting about 13 kg per meter, higher than specified. The desired value is 350 kg per meter, and the actual average value is 365 kg per meter. So here the main problem, before starting we should eliminate the instability. As you can see here, there are instability points here, all over the chart. We have instability points. The problem is that we don't have the sufficient data to go for this. The eliminating the instability, in order to do that, we need the real data from previous production, especially the data for checking the raw material before production. So this is the proposed cause-effect diagram for this case. The main problem is the high thickness, and the categories are raw materials, the machine, the sudden orders and priorities, and the people themselves. So for raw materials, we have for resin, the resin temperature is a factor, the resin viscosity is also a factor. Like for example, when the viscosity is high, we need more consumption, we need more resin consumption. Also when the resin temperature is low, also we need more consumption. For sand temperature will play a main role also, and for sand particles also will play a major role. When we have, for example, small sand particles, also the resin consumption will be more. For glass, hoop tension on the machine will play a major role, and the Chubb electromagnetic charges that is created when we cut the glass rubs. Some magnetic charges will be created, and because of this, sometimes the Chubb will stuck on the plate while it is going to the pipe. It will stuck and not going to the pipe. This will cause also some variation in the Chubb amounts. For machine, the high mandrel OD, outside diameter, and the low mandrel OD, the mandrel rotation speed also, these will play major roles in the thickness. Sudden orders, which I think is one of the main problems for our case. I mean by this is that when we have some high priority orders, we shut down the machine and change the setup for another diameter. And then when we finish, we go back and set up the machine for the previous diameter. This will change some variation in the machine setup, which will cause, of course, the variation in the thickness. The people themselves, as I said, when they deal with the thickness variation cases, many times they don't know what to add and what to reduce as raw materials. So we need to train them on how to deal with such situations, and to instruct the operators to inform the production engineer before taking any action. After modification of the process, if you can see, this raw material check was there in the original process, but I made a thread like this because we need to have the start collecting the data for checking the raw material before production. It will benefit us a lot on knowing the reasons for any thickness variation in the future. And here, whenever we have thickness variation, we need to check, first of all, what is the missing raw material. It's not just adding and reducing any raw material. We need to check, and we can do this either by testing the material composition of the pipe, and QC will help in that, or by checking the machine feeding equipment. Sometimes something is stuck in the equipment itself. Sometimes, the machine is not working, the feeding equipment is not working properly. So there are so many causes that might affect the material consumption. And then we add and reduce the raw material based on the checking results. As recommendations, first of all, I suggest that we go with the instability elimination. We should eliminate the instability by collecting the data for raw materials properties before every production run. This will help us a lot knowing the contributors to the variation in raw material consumption. Also, trying to delay the sudden orders till the end of any production run. This will help a lot also reducing the variation.